Next, we want to prove that this part of the equation, b cosine of square root of k over m times t, is the projection on the x-axis of a radial vector representing the location of a point moving around a reference circle of radius b centered at the origin, starting on the positive x-axis when t equals 0, and the point moving around with angular velocity omega equals square root of k over m. Now, you might want to digest that, but you should stop and do that. Having done so, you should draw a picture of this situation. What do you have in this picture? You have a circle of radius b centered at the origin. That would be a good place to start. You draw one of those round things, a circle, put a point in the center, put an axis through it, an x-axis through it, and you have a reference circle of radius b, and now you consider a point starting on the positive x-axis moving around the circle. And you have a radial vector out to the point on the circle that moves around with the point on the circle like the hand of a clock. You want to draw a picture that represents that. And you want to somehow indicate that the object starts on the positive x-axis and make reference to an angular velocity omega. Then think about what the location of that point would be at clock time t. See how much of that information you can assemble into a picture and into some statements. Well, here's a good picture. Here's a circle which we'll say has radius c. We'll declare radius b. This circle has radius b. I haven't written it down here, but let's just assume that the circle has radius b. Now, in this figure, I've assumed a radius r. So if you want to erase a little part of that b and straighten out a little bit of the one of the legs, you can get an r. In any case, this has radius b, and we want the projection on the x-axis of radial vector representing the location of a point moving around the reference circle. So we assume that we have a point moving around the reference circle. It has a velocity at any given instant, and there's an acceleration. But importantly, for this task, we have the radial vector out to the point. That's the vector r of t, and we project that vector down on to the x-axis. And what is that projection? Well, that projection is just don't have it written down here. I was looking to see if I had it written down, but that projection is just r times the cosine of this theta of t function. Now, theta of t is going to equal, in this case, omega t. So here's your theta of t equal to omega t, and omega is equal to the square root of k over m. So this is then the point. Okay, well, this point then moves around the circle. If we project this point to the x-axis, then the projection is going to be just the magnitude of the r vector multiplied by the cosine of this theta vector. We know, of course, that projecting the vector onto the x-axis is done by taking the cosine of the magnitude of that vector. So if this vector is little r of t with magnitude r, then this vector here, or this position on the x-axis if you prefer, is just r times the cosine of theta of t, which is r times the cosine of omega t, if theta of t is equal to omega t. Now, the condition we have here, omega is square root of k over m, so that theta of t is the square root of k over m t. So we write that as r cosine of the square root of k over m times t. And of course now, if instead of r, this is the radius of the circle is b, this is going to match this. Theta equals omega t because we've started at the positive x-axis when t equals 0, and the angular velocity is omega, so the angular displacement from t equals 0 to whatever t is just this. Projecting the vector, we get the result that we're trying to match. Now, if you instead project the r vector onto the y-axis, and I don't have that in the picture, it would get way too cluttered. If you project this r vector onto the y-axis, then what you're getting is you're getting the sine of omega t, sine of this angle, times the radius of the circle. So that if the radius of the circle was a, you would match a times the sine of omega t, where omega is the square root of k over m. So that we can match either a sine or a cosine with this reference circle picture. Now, if we have a combination of sine and cosine, what does that do?